Okay, in this video we're going to look at the kinetic theory equation, and it's basically this here. It's PV equals a third nm times the mean square speed of the molecules. Now the big confusion really lies in this whole concept of root mean square speed and mean square speed. So to understand that, especially if you're going to try and revise using the textbook, which I think is very confusing, then you've got to understand, start this idea here, this idea here. What does mean square speed mean? Well, mean means average, which is speed 1 plus speed 2 plus speed 3, all added up together, divided by the number of speeds that there are. So that's where the mean comes from, and the square speed comes from the idea that the speeds are all squared. So to find the mean square speed of something, you get all of all the molecules in a gas, you'd let each of their different velocities and square it, and that would get rid of any negative signs, some going one way, some going the other way, and so on. Make them all positive. Then divide it by the number, and that gives you the mean square speed. Sorted. Now the next thing you got to think about is, what does root mean square speed mean? Root mean square speed is the mean square speed square rooted. It's not that surprising really, but what that means is that the root mean square speed squared is the same as the mean square speed. Okay, so we can find the mean square speed. That's fairly straightforward, and we could just write it as mean square speed, and that's written as C bar to mean, average or mean, squared. But in the book they like to write it a different way, and we'll come to that in a minute, what's important about this. So mean square speed, speed of all the different molecules, or the velocities, all squared, and then divided by the number of molecules. That's your mean square speed. Root mean square speed is the square root of all that. Of course, if you square the root mean square speed, you get back to the mean square speed. Okay, with that said and done, we'll move on. Now, the idea to understand the kinetic theory equation, you have to understand, is based upon 5 assumptions, which are really significant. I'm going to point out why they're so significant as we go through. Number 1, they're point molecules, which means they've got negligible volume. Number 2, they do not attract each other. Number 3, they can have continual random motion. Number 4, they undergo elastic collisions. And number 5, each collision time is negligible compared to the travel time between collisions. Now, to understand this, you've got to think about a particle travelling in a box, and it can have a velocity or speed in any old direction we want. The speed of a particle can be broken down to its components in the x, y and z direction. Okay, and therefore just applying Pythagoras in 3 dimensions, basically we'll say the speed squared is equal to the x component of the speed squared plus the y component of the speed squared plus the z component of the speed squared. Now, to understand what's going on with this box, I'm just going to move this over here. To understand what's going on with this gas molecule, what we've got to think of is, we're just going to think about the force applied due to one molecule doing one thing. So imagine we're looking at this molecule, we're only concerning ourselves at the moment with its velocity or its speed in the x direction, and it's moving that way, so that's the x direction. It's going to hit the side of the box, this shaded face, and bounce back. So the change of momentum is final minus the initial, so it's minus mu, okay, and this is 1 because we're talking about the first molecule, minus the initial, which is of course a positive value, so it becomes minus 2 mu. That's fairly easy to understand. But this statement here is based upon the idea of that 4th assumption, that they're elastic collisions, that it's going to come back at exactly the same speed, and that's important. So that's why this is so important, else this doesn't make sense. Next thing is the time between these collisions. When this thing hits the face of the box, it's got to travel, it's going to hit there, bounce off there, then come back again and hit again. So the time between successive collisions with this face of the box is going to be given by the distance, which is there and back, 2L, divided by the speed, which is mu. Now again, this is based on an assumption as well. We're assuming, first of all, our assumption number 1, that they're point molecules, i.e. that the size of this is so insignificant that it's not going to, the distance isn't going to be from the inside edge to hit to the inside edge. It's not going to take off the the diameter of a molecule is not going to affect this length here. That's the key thing we're saying there. Okay, and therefore, basically, and the next thing to say is that affects this is that they do not attract each other. Point number two, i.e. because they don't attract each other, they're travelling in straight lines and not hitting into each other at all. So the speed is going to stay as u all the way across. It's not going to change as it affects anything else. Okay, anyway, this is the proof you want to go through for your exam. Time is distance over speed, so it's twice that length there divided by the speed. We've got change of momentum, we've got time between them, so we can work out the force. Newton's second law. Force is change of momentum divided by time taken. We'll use our change of momentum from up here, which is minus 2mu1, and we'll divide it by the time taken, which is of course 2L over u, which is down here on the bottom. Putting the u up there, we get minus mu squared over L. The 2's cancel out. Now that's of course the force acting on a molecule. It's still got a minus sign in it. Therefore, the force acting on the box is going to be the opposite direction, so we can get rid of the minus sign for that. Now, if we want to use it for work out the pressure, then force over area, we have this term here, and we're dividing it by the area, and it's length that way, and length that way, so it's length squared. Now length is basically the volume of our box here. And so what we have is the pressure is now minus 2mu squared, or I could really drop the 2 at this stage because let's say it's the pressure on the box, is mu squared over v. Okay, the volume of our box. And that of course is the pressure on the side due to just one molecule colliding into it. Now, if we wanted to work out what it would be for n molecules, let's say there's n number of molecules in the box, then what we really want is to get rid of the square of the speed for one molecule and replace it with the average or the mean square speed of all the molecules, the mean square speed of the molecules multiplied by the number of molecules. Okay, because they're all different volumes and velocities. So we'll say the pressure is now equal to the number m over volume times the number of molecules times by the mean speed squared, okay, or mean square speed of the molecules in the u direction. Now here's the weird thing, is what we could say here is, if we wanted to, because this is just in the x direction, we've got to think about what the pressure is due to the y components and the z components. Okay. Now, therefore, we just use this little sort of sheet here, if you will, not cheat, but a statement of fact that the mean squared speed, okay, altogether the mean squared speed is the mean square speed in the x plus the mean square speed in the y plus the mean square speed in the z. So we really just want to shove that term there in there, okay? And of course that is going to be 3 times as much as these lots, so we're going to use a third of this is equal to one of these, just one of these. So we've got to basically say divide it by 3 and put in the mean squared speed. Now at this stage what we should really do is just put in c bar 2, because that is the mean squared speed, but for some reason the book, they don't like you doing that. And the book, you know, in the textbook proof basically says, and this is what's in your formula sheet and everything as well, is pressure times volume is a third nm times the root mean square speed squared. Okay, so it's the root mean square speed squared. Now what that actually means is that this lot together just gives you the mean squared speed. Okay, so going back to what we said at the very start over here, okay, that the mean squared speed is that plus that plus that over that, and we could write it like that, okay, and we can quite easily say here that that is that plus that plus that. That makes this whole idea of just switching to the 1/3 quite straightforward. And so if you want to do the proof, you should be able to get to this stage fairly easy. You could then probably just say, well, P equals a third m well, m over 3v, should we say, times by n, and then just put in c bar squared, and that would actually get to the end of this equation. That would probably do in the exam, and leave it at that, okay, because that's the mean squared speed. But in your formula sheet and in the book and the AQA way, they like to do it to say it's c times the root mean square speed squared, which is this lot all together. This whole term together is the mean square speed. Hopefully that makes a bit of sense.